Welcome everybody to day 2 of POPL. I'm really pleased this morning to welcome our invited speaker for today. This is Armando Soledad-Zama. He's a professor at MIT and associate director and COO of CSAIL. He's best known for his work on program synthesis and the development of the Sketch program synthesis system. He's recently turned his attention to working out connections and synergies between machine learning AI and program synthesis techniques. He's currently the lead PI of an NSF-funded expeditions project, Understanding the World Through Code. And he's also the founder of playscript.com, an online presentation platform for creating interactive presentations. And I'm told that today's presentation was built using PlayScript. So Armando, take it away.
Thank you. Yeah, so I created all the slides with the language and platform that I wrote myself, which is probably not the best idea. So if it's a little glitchy, apologize. But hopefully it will work. So I want to tell you about some of the work we've been doing recently at this intersection between programming languages and very specifically program synthesis and machine learning and AI more broadly. And so a lot of the early work in my group was really revolving around this paradigm of syntax-guided synthesis. The high-level idea was that we wanted to generate code, and we didn't just want the user to tell us, hey, here's what the code is going to do. Those behavioral constraints are certainly very important, and we really like techniques where you can specify these behavioral constraints in ways that are natural for users, things like input-output examples, but also things like safety properties and even formal specifications. But a key idea behind syntax-guided synthesis is that you can combine this with constraints on how you want your programs to look like, information about the structure of the code, things like sketches, but also things like just a set of components that you know your program has to be built upon. And one of the things that makes this idea very powerful is that by combining information about what you want the code to do and information about how you want it to do it, you can actually get away with synthesizing some interesting things. And so today, this area of program synthesis has advanced quite a bit thanks to the work of a lot of people in this community. For example, things like data structure manipulations, even synthesizing fairly non-trivial data structure manipulations and even verified implementations of these can actually be done fairly reliably with some of the newest program synthesis algorithms. Data wrangling is also a domain where we have seen a lot of success in terms of being able to take messy data and implement, by example, transformations on this data. Flash fill in Excel is probably the best example of these. This was a project that was led by Sumit Gulwani at Microsoft Research. However, in addition to the applications to what you might consider programming or software engineering, there's also been, almost from the very beginning of this field, a realization that a lot of the techniques that we're using for some of these software engineering or programming goals could actually have broader applications. I think the first paper to really realize this was this paper in 2010 by Susmit Jha and Sumit Gulwani and Sanjit Seshia and Ashish Tiwari, where essentially what they did was they turned the program synthesis playbook on its head. They said, look, normally, the way you think about program synthesis is that a programmer comes in, gives you a specification, and the job of the synthesizer is to give you an implementation. But what if we did it the other way around? It turns out there are many situations where you have an implementation, there's some blob of code that somebody handed to you. And what you're really trying to figure out is, what is this code doing? How do I go from an implementation to a specification? And it turns out this problem can be attacked using the exact same program synthesis techniques that you use for the other problem. And in fact, the situation that they were focusing on in this paper was one where this implementation is just a black box. It's completely opaque. The only thing you can do with it is provide it inputs and outputs. And so the role of the synthesizer is to take these inputs and outputs that came from the implementation and generate a specification for that. So in the case of this paper, they were looking at obfuscated code and trying to figure out what this obfuscated code is going to do. But this has turned out to be a really powerful idea. For example, we've seen several papers in the community that are looking at different instantiations of this idea. For example, Patrice Gaufreau led this paper all the way back in 2012, looking at, hey, if you look at execution data from instructions, you can actually generate a model of what a particular instruction is going to do. And you can use that, for example, to do symbolic execution. There was this other paper with Stefan Huel and Manu Sridharan and Satish Chandra, which was looking at, hey, if we look at inputs and outputs from an API, you can generate a model of that API. In fact, we did something similar with Jeff Foster and some of our students and postdocs at the time, where we were looking at reactive frameworks, right? And the idea is, for example, when you have something as complicated as, let's say, the Android framework, it can actually be very difficult to run program analysis over that framework. But if you get a set of test applications and you record how these test applications are interacting with the framework, all the messages going back and forth between the application and the framework, and combine that with your structural knowledge of design patterns, then you can actually get a simplified model of this reactive framework that doesn't capture all the complexity of the real Android API. It's not supposed to. It's supposed to be a model. In our case, we're particularly interested in the reactive behavior of these APIs, the fact that there are certain objects that when you register them, later they call certain methods. So being able to build these models from these input-output examples turns out to be a really powerful thing. But all of these works are still in the space of, essentially software engineering applications, right? We're still looking at synthesis in the service of helping us write code, helping us analyze code. I think the really big leap came when we started looking beyond programs. And to me, at least for me, the really influential paper in this space came from Raz Bodek's group back in 2013, where they actually took some of these synthesis technologies and applied them to understanding metabolic pathways in a worm. The idea being that what you have are all of these actual wet lab experiments that give you a lot of information about how things interact with each other. The kind of things that you're interested in are these regulatory networks where the presence of one chemical promotes the creation of another protein or enzyme, and that promotes the creation of another protein or enzyme, or it might inhibit the production of a protein or enzyme. And so what you're looking for is to understand these network, and the process by which it inhibits or promotes often can be represented as a state machine. And the really remarkable thing about applying synthesis techniques to this was that you could actually take the results of experiments and ask the synthesizer not just to generate for you a hypothesis that matches those experiments, but you could ask the synthesizer to generate for you multiple hypotheses that match those experiments. And you could then design new experiments to disambiguate between those different hypotheses. You could actually ask the solver to tell you what experiment you need to run in order to tell whether alternate mechanism A is the right one or whether alternate mechanism B is the right one. And I think this really opened the imagination of the community as to the kinds of applications that you could have of this particular technology, really going beyond software engineering applications into understanding things out in the world and being able to reverse engineer things out in the world by leveraging program synthesis techniques. So we've done similar things in other contexts. For example, one domain that is actually pretty exciting is in linguistics. Being able to take, for example, a collection of words in a language and being able to infer morphology rules and phonology rules out of those things. We actually started doing, we published some early results in this work led by Kevin Ellis with Josh Tenenbaum all the way back in 2015. We're actually putting together a journal paper around this. Another domain that we have been very excited about is computer-aided design, where sometimes one of the things that you want is you have a solid object. This might be a solid object that you actually have in the form of a chunk of metal that you are trying to figure out how to reverse engineer, or it might be in the form of a mesh that, yes, it's in digital form, but it's lost all the information about how it was created. And what you're trying to figure out is what is the sequence of geometric operations that can help you produce that, that form. And so we've actually been doing some work in this space in collaboration with Wojciech Matusek's group at MIT. In fact, our first paper on this was led by Tao Du, and we showed that basically just using our sketch synthesis infrastructure, you could actually generate these kind of decompositions, even for fairly intricate mechanical designs. So that was pretty interesting. The more we started pushing in this direction, though, the more we realized that the synthesis techniques that we had available to us and that we had been developing over the years had some pretty significant challenges when attacking these kind of problems. Scalability is a really big one, right? It helps when you can decompose the problem into lots of tiny problems, but oftentimes either you cannot do it or you can only do it at the cost of losing some fidelity in the model you are going to generate, right? The scale of models that we can produce using our traditional solver-based synthesis techniques are just not that big. The other problem that you run into is that as soon as you start interacting with the real world, as soon as your data no longer is no longer generated by software, but is generated by the real world, right? Even if you're scanning a chunk of metal, you have error in your scans. When you are dealing with language, right? Language always has exceptions. It's exceptions are just an inevitable feature of language. And forget about biology. In biology, it's all about handling noise. And so the kind of techniques we had available to us were really not set up for doing this. And the other challenge that we found is that in many of these, I dare call them success stories, applying synthesis in many of these domains, they came at a pretty high cost of essentially graduate student years, of really hand engineering the space of programs that you're going to search on, hand engineering strategies that you're going to use to search that space so that you can reliably find programs in these domains. And so this is where we started becoming really interested in this intersection between programming languages techniques and the kind of techniques that came from our world and techniques in machine learning. And one of the things that is our goal here is to go beyond just, oh, there's this new deep learning hammer, and let's see how it can help us. What we're looking for here is really an integration of techniques coming from PL, techniques coming from machine learning, not just to help us do better at software engineering problems, but actually even attacking some of these problems that traditionally have been thought of as being in the domain of machine learning. And so how do we do that? So the first thing that we need is we need different kinds of methods for searching over programs, especially programs that incorporate quantitative objectives and programs that have to deal with noise, programs that have numerical parameters. And so there's actually a whole space of neurosymbolic program synthesis techniques that we have been exploring as part of this work. In this talk, I'm going to focus on a particular class of techniques called neural-guided search. And the basic intuition behind neural-guided search is as follows. In traditional synthesis, generally what you're after is exhaustive exploration of a space of programs. And because it's exhaustive, the bigger the programs, the larger those spaces become. And so generally there's a brick wall of how far you can scale these techniques before that exponential just kills you and you're not able to search any further. And so if you have a program that is just out of reach, beyond that horizon that you can search efficiently, you're just not going to find it. The idea with neural-guided search is that essentially you're not going to be searching exhaustively. That search is going to be directed by a neural network, in this case, that is actually going to be distorting that search space. It's going to allow you to search really, really deep in that space and potentially discover some programs that are way bigger than what you could have discovered through these exhaustive techniques, at the expense that you might have a program all the way out here that you could have discovered with exhaustive search, but just happens to not look like the same programs that you trained on, for example, right? As soon as you're relying on a neural network, you're at the mercy of your distribution. Now, how do you actually do this? So at a very, very high level, sort of the 10,000 feet level of this, is that you have a neural network that gets some encoding of what your goal is, what's that treasure you're trying to find, and it gets also something that tells it about the current state of the program. And essentially what this neural network does is it makes a decision about what to do next in this program, right? And this strategy is compatible, for example, with top-down search, where you are essentially building an AST from the top down and adding more and more details into your program. But you can also apply this strategy for any other approach that you might use to construct your program. And so the question is, how can insights and ideas from PL and from the earlier stages of program synthesis research help you in this way, help you make this better? So there are some obvious ways. For example, as you are constructing these programs, one of the things that is just invaluable is if you find that you're constructing a program that doesn't type check, discard it. Pick a different program. The types actually give you a very, very powerful way of ruling out bad programs before you have to complete them. right? Very early before you get to the point of trying to figure out what the details of those programs are. But there are other more subtle ways to make use of what we know from program synthesis. So to give you an example, one of the strategies that has proven to be extremely powerful in constructing programs and generating programs from more complicated languages is the strategy where you do a bottom-up search. Essentially start from the leaves of your AST and start constructing things from the bottom up. But take advantage of symmetries. Take advantage of the fact that on your target inputs, some of these programs might actually produce the same output, and therefore you don't have to keep them all. So to give you a really simple example, suppose that you have this trivial language, right? So what do? You have a constructor for an empty list, you have a couple of numbers, a couple of variables, and then you can get an element from a list, you can add either integers or concatenate lists, and you can append something into a list, right? It's a trivially small language. All I have, if I look at the possible leaf nodes in my AST, there are only 5 possible leaf nodes. But then already from those 5 possible leaf nodes and these 3 operators, there's actually a pretty large number of combinations of ways in which I can combine all of them. But the key insight here is that, yes, there are a very large number of possible combinations. But first of all, most of these combinations are just going to fail, right? If I want to get the yth element from X, well, Y is a list and X is a number. That just doesn't type check. It doesn't generate anything. And but also, many of these combinations actually give you the exact same values for this input. It means that if I'm going to further construct things from that, then I don't have to keep around all those variations. I only have to keep around one representative of the programs that are going to generate these values. And so even though there's a very large number of combinations, you can see that the number of distinct values that I can generate is actually quite small. So that's something that in, I think I can now call it classical synthesis, even though it's not that old. But in classical synthesis, this is something that is very, very powerful and widely used. The first instance of this was actually came from a paper that Rajiv wrote a few years ago. So how do we leverage that in the context of neural-guided synthesis? Well, so what you want to take advantage of is the fact that programs have many symmetries. Oftentimes, there's lots of different program fragments that actually produce the exact same output. And the program state essentially abstracts them away. If I know that this particular sequence of code is going to generate this state, really the only thing that matters, especially if you're doing this bottom-up search, is what is the state that it's going to produce. And I can abstract away all of these variation in the program because they are all just going to produce the same state. And so what we showed is that when you're doing neural-guided synthesis, you can actually take advantage of this. So let's say that you start with an initial state. Let's say that we want a program that is going to generate this shape right here through some combination of geometric operations. So I can have my initial state. The key is that at any given point, the neural network doesn't actually get to see the program. It doesn't get to see code. What it gets to see is this is the state produced by the program so far. And from that state, can you predict what is the next operation that we should do? And so, for example, here from this state, it decides that you should produce a rectangle. That command now goes through an interpreter to produce a new state, right? And so now the neural network doesn't actually get to see what command you produced. It doesn't care whether this was produced just by drawing a rectangle or whether it was produced by some complicated piece of code that eventually ended up just generating this rectangle. What matters is that you have this rectangle. And so what are you going to do next in order to get to your goal? And so now it can decide, okay, let's go and produce a circle, right? And now it can decide, let's go and subtract the circle from the square. The point is that in the traditional neural guided search, where the neural network essentially has to learn how to interpret a program. It has to learn, this is the code that I've produced so far. What is this code actually going to do? How does it differ from what I want to do? Here, we're relying on the fact that there's really no need to try to get the neural network to learn how to interpret programs. We already know how to interpret programs. We have interpreters. These programs have very clean, well-defined semantics. Let's just run them, see what they do, and then use that as the thing that we are feeding the network. And so in that way, the network doesn't actually have to learn how to interpret code. It just has to know from this state, what should I do next? Right? Never actually having to see the program means that it can abstract away from all these variation. And that turns out to be pretty effective. For example, in this domain of geometric programs, you find that compared to a baseline that isn't trying to do that, that is just trying to spit out the code all in one go without ever looking at what that code is going to do, you can actually do much better. You can see that it's not perfect. Here, for example, we're missing the little hole in the key, but it can get pretty close. One of the problems with the more traditional approach, where you're trying to generate the full program without ever seeing what it's doing, is that if the program starts going wrong, you're toast. And one of the things that makes programs very challenging compared to, say, natural language is that you're always just one token away from complete garbage, right? A program can be one token away from being the right program, and it might either not compile or crash or kind of work, but not really, or even, depending on what language you're using, it might work, but also have major vulnerabilities. So having this ability to actually analyze the program as you go, execute it, see what that program is doing, and use that as the basis for the network can actually give you something quite powerful. We can also generate, for example, 3D shapes. And we can even follow the same strategy for text, just these kind of text manipulation problems, where you want to give a few examples and you want to generalize with something. We actually compared this approach, and there's a little bit more to the details of it in terms of how we actually do the search and how we leverage the neural network to do a search for the program that actually works. But we can see, in general, much better generalization. So here in this plot, what you're seeing is essentially the blue line is the best version of our algorithm, and essentially the purple line here corresponds to prior work, and the lines in between correspond to different variations of the algorithm. I'm not going to go into the details of them, but this is really just one example of how we can take an idea, an insight that was, hard-earned knowledge from working on these problems in a completely symbolic context, and leverage it in the context of a neurally guided search in order to produce an algorithm that is going to do a better job at generating the programs that you want. And there's many other examples of these, including, for example, approaches for incorporating the more exhaustive styles of search that we know how to do really well from the more classical synthesis algorithms and incorporating them into the search. But what can you do with this, right? So if we're interested, again, not just in attacking software engineering problems, but on the kind of problems that people in other communities might care about. So this was actually a paper in NeurIPS 2020 that arose basically from Josh Tenenbaums and my student, Maxwell Nye, spending a summer working with Brandon Lake at NYU. And here, the idea was to look at a particular class of generalization problems where people are actually quite good at them compared to traditional machine learning algorithms, which are actually quite bad at them. And this shouldn't be surprising because these are really very symbolic kinds of problems that even though neural networks like to pretend that they're good at symbolic things, they're often not as good as actual symbolic reasoning algorithms. So in this case, the problem is as follows. Essentially what you have is you have these completely made up languages. And your goal is given some tutorial examples, kind of specifically crafted for illustrating how this language works. You're looking at the ability of a learner to figure out the basic logic. So for example, here, what I have are some primitives that draw some dots of different colors, right? And then I also have some functions that do certain things, right? So for example, I can see that there is this function called FEP that if I apply it to log, then it's going to generate 3 copies of these, right? And I can look at these examples and make hypotheses about exactly what the semantics of these language are, right? So for example, I can generalize from these 2 examples from FEP to say, yeah, FEP probably takes whatever that thing before it is doing and just does it 3 times, right? And so what you find is that from examples like this, with their own composition rules, their own functions, just explained through a very small set of examples, people can often do a pretty good job of learning what, of generalizing and figuring out how other examples are going to behave. So for example, if I now give a random sample of people, so in prior work from Brandon's lab, they actually showed that humans are pretty good at figuring out these generalizations. On the other hand, traditional machine learning approaches, not so much. And in particular, for example, a kind of state-of-the-art approach for doing this essentially consisted on taking a set of examples, encoding them into some embedding that describes what those examples are doing, and then using that to do to drive a neural translation that says, from this input, what should the output be? And turns out that this kind of approach has a really hard time generalizing beyond the examples that it has seen. By contrast, the more synthesis approach is to say, okay, what we're going to do is we are going to use neural guided search, essentially the kind of techniques that I described earlier, and we are going to generate candidate programs. And we can actually run those candidate semantics for that language. We can actually apply them to those programs and see what they do and find the target semantics that actually matches those examples. And that is the one that you can now return and use it to generate new outputs for new input programs. And essentially what you find is that even in a pretty hard set of these this problem, our approach can actually do quite well compared to the kind of generalizations that the neural network is able to do, especially if you're asking the network to generalize far from the examples that that it was trained on and from the kinds of examples that it was trained on. Interestingly, kind of cute applications of these was looking at number words, right? And essentially the algorithm for taking number words and converting them into actual numbers. And it turns out you can actually describe that as a little semantics for these simple programs, and essentially from examples of number words in different languages, you can actually get some reasonable success in translating number phrases and number words in different languages, even when compared to a neural approach that is trained on really, really similar problems. And so the high-level idea here, the take-home point really is that if you're solving a problem that at its core is symbolic and requires symbolic generalization, symbolic techniques have a lot to offer beyond what you can do with more sub-symbolic techniques. Another example of the kinds of things you can do once you bring together these ideas from traditional program synthesis with ideas from learning is in this paper that was led by Jivan Inala. It was published in iClear 2020. In this case, what we were looking for was policies to control simple mechanisms, but we were interested in policies that have repetitive behavior, repetitive structure. So a neat, very visual example is this, I have a car and I'm trying to get out of a parking space, right? It's just parallel parking, I'm trying to get out of it. And if the parking spot is tight enough, I'm going to have to go back and forth a few times before I'm ready to escape. And the tighter that parking spot is, the more times I'm going to have to do this iteration back and forth before I can leave. Now, what you want is you want to be able to say, here are some training examples. Here are some scenarios where I want my policy to work. And what you want is you want the system to actually learn a policy that doesn't just work for these scenarios, but work for scenarios that potentially require you to extrapolate pretty far from the observations that you made. And so in this case, what you really want is that from these training examples, once you go to a scenario that is much, much tighter than what you were trained on, the system will know that it just has to go back and forth many more times before it's able to escape. Now, what happens if you just train a deep neural network using reinforcement learning in order to get this kind of a policy? Well, the problem is, if you only have these initial 3 scenarios, you're going to get a policy that works pretty well for these 3 scenarios. But you can already see in the behaviors from the policy that this is not doing the kind of repetitive behavior that you would expect. At every step, it's sort of doing something that eventually it gets it to reach the goal. And it might generalize a little bit, but once you are in a situation where that really looks very different from this training data in terms of how tight the space is, then you are now just crashing back and forth all over the place, right? Because this just looks really different from what the network was trained on, and there was really nothing in that structure to convey the fact that you actually want these generalization. And this is where we go back to the idea of syntax-guided synthesis. the idea that by restricting the space of functions and the space of programs that the system is able to consider, you can actually force certain kinds of behavior and certain generalizations that are desirable. So in this particular case, what we find is that when you're interested in this kind of repetitive behavior, these kind of finite state hybrid controllers can actually be very, very powerful. So the idea here is that your controller is structured around a set of discrete modes. And at every mode, you have a continuous function that is going to tell you how you're supposed to behave in that mode. But you also have these predicates that when these predicates are satisfied, they force a transition to a different mode where the system is now controlled by a different function that is going to do something different again until you satisfy one of these guards. And so with this kind of structure, it's actually very easy to get repetitive behavior because you can get these loops in the structure. The challenge is learning something like this completely from scratch, just from training from those examples that we saw before. Because the challenge here is that now what you have is you have both discrete structure in the form of the individual modes, their connections, and the predicates associated with every one of these transitions. But you also have continuous parameters that actually govern what's going to happen in each one of these modes. So once you have those things, it becomes a really different search problem from the kinds of search problems that we're used to solving in the more traditional program synthesis context. And so the approach that Jivana came up with is based on a teacher-student algorithm. And the basic idea is as follows. One of the things that makes deep neural networks actually work, even when, in reality, they really shouldn't. They're trying to solve a very hard nonlinear optimization problem. But one of the things that helps is that they're so over-parameterized that they tend not to get stuck in undesirable local minima. By contrast, if you already say, here's my structure and here's how I want my program to look like, and I just want to solve for these parameters, it's very easy to get stuck in local minima. We've learned that the hard way by trying very hard to use numerical optimization in the context of discrete programs. So instead, the idea is that we are going to start with a function that is an incredibly relaxed version of the function we want to find. In particular, what we have here is we are optimizing not what happens in individual states, but we're just optimizing a sequence of actions, right? What is that sequence of actions? Who cares? Every step in that sequence has its own distinct parameters. It can do whatever it wants. You have a very large number of parameters in this problem. And what you're solving for is a trajectory that solves the problem. Now, once you have that trajectory that solves the problem, what you want to do is you want to go back to the student and tell the student, hey, can you come up with a state machine that matches that trajectory, right? Now we know exactly what has to happen in each state. Now we're just looking for a state machine that does that, right? So how do we do that? Essentially, what you have is the teacher learns this loop-free policy. It's just essentially straight line code, doing something potentially distinct at every step. And what we're going to do is we're going to look for actions that look similar, right? Not necessarily identical, just they look kind of similar. We're going to cluster them. And we're going to say, yeah, those are going to kind of correspond. Those are going to correspond to the state in our state machine. And so that means that we are going to have these transitions from one state to the other. And we're going to try to come up with just one function and some predicates that take us from one state to the other. Now, in practice, this is not going to work. We're going to get we're not going to be able to match what this completely unconstrained policy produced. But what we're going to do is we're going to take the best we can find, the best solution we can find. And so now the student goes back to the teacher and says, well, I couldn't do what you asked me, but I did this instead. And so now what the teacher is going to do is it's going to look for a new trajectory that, in addition to reaching the goal, it's going to try its best to match what the student was doing. It's going to try to adapt to the structure that the student discovered. The idea being that the next time around when the teacher produces a new trajectory, it's going to have a better chance of actually matching the structure that the student is able to produce. And so in this back and forth process, what you get is the meeting in the middle and being able to find this hybrid controller that actually gets you the behavior that you want. And so what we find is that in many of these different scenarios, when you look at just the training scenarios, you're able to find policies that work reasonably well as the policies that we found with reinforcement learning. So these are not particularly hard problems. The hard part is not finding a policy that works. The hard part is that as soon as you try to generalize to a different scenario that requires this extrapolation, that requires going beyond what you observed in the data, the policies that have all this structure hold much better than the completely amorphous and unstructured policies that that you discover through deep learning. So these are just a couple of examples of the ways in which you can get better learning by leveraging some of these techniques that have been developed, not just in the program synthesis community, but more broadly within our space of programming languages and formal methods. A lot of these ideas are actually the basis for this expeditions project that we launched, essentially with the goal of looking at leveraging these neurosymbolic techniques for scientific discovery. This scientific discovery domain is one where you really care about things like interpretability. You really care that the models you discover don't just make predictions, but are also consistent with all this background knowledge that you have about the world. And it's a pretty large project involving many PIs that you know and love, and some that you probably don't know, but if you knew them, you'd love them too. And essentially what we're looking at are applications of these kind of ideas and this kind of techniques in 4 particular domains: organic chemistry, RNA splicing, cognitive science and behavioral modeling, and computer systems, right? And the last 2 domains are somewhat in the spirit of some of the things that I showed in this talk today. I'm happy to also tell you some of the early things that we're exploring in the first 2 domains offline. But I think to conclude, I think there's a really big opportunity to take some of the things that we really know how to do well in this community, to do very sophisticated symbolic manipulation and automated reasoning, to leverage ideas about structure and modularity, and to deploy them beyond our traditional software engineering and programming contexts in many of these other domains where I think these ideas can be very, very powerful. And so with that, are there any questions?
All right, let's thank Armando. Any questions from the room? I'll come to you with the microphone.
So you mentioned some approaches like neural guided synthesis and other synthesis techniques, but these techniques help to, the synthesis be faster. But is the generated program has the high quality? I mean, readability, explainability, understandability, and maintainability. If the programmer don't know these quality, don't see these quality factors, does he use the code? Or if he don't know why the program satisfies the spec, does he use the generated code?
So those are really good questions, and I think these are questions that we're still grappling with in the community. So one of the advantages of formal techniques is that oftentimes you can make guarantees about the code you produce. So it might not be readable, but if you can prove it correct, then you trust it all the same. Neural guided techniques, on the other hand, have the advantage that they generate code that looks like the code in the training set. And so it can replicate a lot of the nice structure of the code in the training set. It can also replicate some of the devices and problems in the training set. People are certainly seeing that now that they're looking at these very large language models for generating code. All the vices of bad coding practices that you see on GitHub are happily replicated by the neural network. I think the combination of both is where you can get a lot of power. So that, yes, you can get the style matching that you get from the neural techniques, but also have some confidence that you're not going to get just garbage that happens to look like code, but having some confidence that what you get is actually going to run and it's actually going to do what you want. But the exact ways of how you get there, I think some of the ideas that I discussed here help, but I think there's still more work to do.
Okay, we have a question, a remote question. This is from Jesper Cox from TU Delft. And they ask, what makes a PL better suited for program synthesis? Should we be designing languages specifically for program synthesis?
That's a good question. The number one thing is conciseness. Right? The big barrier for us in program synthesis is scalability. So the more you can say in a small amount of code, the more powerful your system is going to be. There are some ways in which, especially the more traditional techniques, differ so greatly from how we normally think of as programmers that a lot of the cues that we use when reading code to help us understand what this code does, by and large, especially the more traditional synthesis algorithms are not really looking at. So you can get away with a language that looks ugly and unreadable as long as it's compact and has all the right things. But I would say the number one thing is really conciseness.
Okay, thank you.
Thank you for the excellent talk. Both with REPL and the student-teacher model, it looks like that you mostly look at one input-output pair, which you then first try to approximate or synthesize a program for. How do you deal with situations where you want to define or synthesize a program that deals with multiple input-output pairs, so that perhaps matters what happens under the hood and not just the result is what you're interested in?
Okay, we have another question in the room.
So one of the main things about the structural constraints in syntax-guided synthesis is the design of DSLs or meta-DSLs for producing DSLs. Now, in the task that you've shown, it's fine because there's evident structure, and you can and should take advantage when you see it. But in the scientific task that you mentioned at the end, it's not sometimes clear what the formalism is, and so you might have to discover these what might not even look like DSLs with learning techniques rather than being able to hand design them because formalisms are unclear. So could you comment on what happens then?
Synthesizing abstraction, starting from a very, very low level language and using a combination of learning and symbolic reasoning. Oh, all right. Well, so for the people remotely, I don't know if you heard the first part of what I said, but just to summarize, having this ability to generate your own abstractions is really, really important and really powerful. And we're starting to develop approaches to do that. It's still at a very early stage. I mean, there's one paper at this point, but it points the way of how you can actually leverage data and this combination of neural and symbolic techniques to build your own abstractions based on the data rather than relying on completely hand engineering of these problems. Now, that means that you lose some of the data efficiency that some of these techniques have, but in exchange for that, it also opens the possibility of discovering things that might be more unexpected.
Okay, and we'll finish with a question from online. Actually, there's two questions, but I'm going to kind of synthesize them, and they both have to do with the question of training. It's well known that training data needs to be plentiful for deep neural networks to work. And what are the challenges with that in the sort of PL synthesis space that you've experienced?
So that's a very good question. So on the one hand, one of the advantages of the more symbolic technique is that by virtue of bringing in a lot more structure and a lot more domain knowledge, you can generalize with much fewer data. We sell that as an advantage, but it's also partly masking the fact that purely symbolic methods don't scale. It's very hard to generate things that are trained on very large amounts of data. At the same time, there are techniques that you can use to ameliorate that, right? After all, we solve in the classical synthesis setting, we solve problems that are quantified over all data, right? All possible inputs, right? I mean, what can be bigger than that? It's it's way bigger than any data set. How do we do it? Well, of course, we don't look at all of them at once. We have developed techniques that allow us to focus on different things at once. And in some ways, neural networks do similar things, right? They train in batches. They don't actually look at the whole data all at once. And so I think one of the things that we're learning to do is better approaches to batching and better ways of focusing on different parts of the data one at a time and building up complex solutions from the things that we learn from smaller amounts of data. It's still at an early stage. I think there's still a lot of work to do, but I think there is a path.
Okay, and with that, let's thank Armando again.